I think that's good enough. I think we'll go ahead and get started. So what's up, everyone? My name is Constantine. I'm part of the New York cohort. And today I'm going to be presenting a paper on a constructive approach for one-shot training of neural networks using Hypercube-Based topological coverings. So I know that's a mouthful and it seems really complicated, but as you'll see as we go through, it's actually pretty straightforward. You can find the link to the paper down here. So there we go. What is this paper about? So in general, it's about sort of a novel constructive approach for training a simple ReLU neural network using geometric approaches. So if we define that a little more, if we have a set of data like this, and just for the rest of this presentation, I'll be focusing mostly on 2D examples, but this method does extrapolate to higher dimensions. And when I say neural network throughout this presentation, I'm referring to a straightforward multi-layer perceptron. So just fully connected layers, right? No recurrent nodes, no LSTM stuff, no convolutions, nothing like that. So just a straightforward multi-layer perceptron. So if we have some data like this, for example, some two-dimensional data, we can construct a topological covering, and in this paper, they focus specifically on using hypercubes, right? This topological covering, when you use hypercubes, directly specifies a set of linear matrix inequalities, and this set of linear matrix inequalities can be used to construct a ReLU neural network, both the structure and the weights. So this process is basically what this paper details. And they show that this approach is able to train neural networks in one shot, which is slightly misleading when they say it like that, but I'll explain why later. And they are able to achieve equal or greater performance while reducing training time. And once again, the results that they present there are also slightly misleading, but I'll get to that later. So why is this important? When it comes to multi-layer perceptrons, just straightforward, fully connected layers, there is no algorithmic approach or sort of constructive way for determining the proper architecture or the proper structural characteristics from either the problem or the associated training data. So if you are given a set of data and a problem to solve, and it needs to be solved using a straightforward MLP, it's just kind of trial and error, right? Like you have to, you usually start with like one hidden layer with like 32 nodes or something, and then you optimize that, given your hyperparameters, and then you try some other, depths and sizes or number of hidden nodes until you eventually either find a solution that you like or, reach something that you think works best. And so within a single choice of a network topology, so if I say, one layer with 32 nodes, this can be optimized, right? But it requires a nested series of optimizations, something like population-based training or grid search. And while there are, ways of initializing weights, they're just initialized so that the training works well. They're not initialized in any way that has a relationship to the actual training data, right? And moreover, a lot of the algorithms that you use to then train a network that's had weights initialized like this rely on gradient information and, like backprop algorithms. And these can become stuck in a local minima, right? Which limits the predictive quality of the network for a given training instance. And another thing is, we don't really know when it's stuck in a local minima, right? For some problems, you might be able to say, okay, I know that, the threshold of performance is here, so I can expect the network to do at least this well. But oftentimes, you have no idea when you're in a local minima if it's local or global. And if you're dealing with data that has a high AD ratio, so a high attribute to dimensionality ratio, the same structural topology, right? So if I reinitialize the weights of a neural network and train it again, the results can vary wildly, right? Because that's one of the problems with data that has a high AD ratio. So attribute to dimensionality here basically means if your data is tall versus if your data is wide. So tall data, you have a few attributes and lots of examples. Wide data, you have a lot of attributes like high dimensionality, like hundreds or thousands of dimensions, or only a few examples. The omniquant data set is a good example of a wide data set, so something that has a high attribute to dimensionality ratio. And the MNIST data set is a good example of something that is a tall data set because we have lots of examples of each of the digits. Wow. So again, if you're dealing with high AD ratios, straightforward MLPs oftentimes suffer from not producing the same results, even if you initialize them basically the same and then retrain using these gradient information methods. So given that straightforward neural networks suffer from all these problems, the question is there a way of getting around this? Is there a way of saying, given my data and my problem, I know that I should structure my network like this with these given weights? And that is basically what the authors propose. So in a nutshell, one or more topological covering maps, in this case hypercubes, are defined between the network's input and output spaces. So the input here would, for instance, be all these random data points, and the output space would be the color of the respective data points, right? So this is a 3-class data set. So we want to define this topological covering so that based off of where a data point exists within the topology, we can say, okay, it belongs to this class. Once you have this topological covering, they basically have a one-to-one relationship with a series of linear matrix inequalities if these are hypercubes, but we'll get to that in a second. So if these are hypercubes, they directly specify a set of linear matrix inequalities. This set of linear matrix inequalities then also has basically a one-to-one relationship with a neural network that uses ReLU activation functions. So this set of linear matrix inequalities not only tells you the structure of your neural network, but it also initializes the weight. And so one of the important things to note about this approach is when we talk about training, this is the actual training process, right? So it's figuring out, how do I get this topological covering? How do I get the best, bisection of the geometry or the topological space so that I can get these linear matrix inequalities? Once you have these linear matrix inequalities, you're done, because they have a one-to-one correspondence with a neural network, and there is no training on this side, right? The weights are initialized so that once your network is built, you can just run data through it and it will classify it for you, which might be a little confusing now, but again, we'll touch more on that later. So it's important to understand what a hypercube is to understand why this works. So a hypercube is just any n-dimensional analog of a square. Technically, it can be one-dimensional too, but then it's not any type of a square. It's literally just a lower and upper bounds. So any n-dimensional analog of a square, right? So this is a 2-cube, this is a 3-cube, and this is a 4-cube, because hypercubes are also commonly referred to as n-cube or an n-dimensional cube. And one of the properties of hypercubes that becomes important later on is that they are convex n-gons that are bounded by 2n n-1 dimensional hyperplanes. So let's dissect that sentence for a second. Convex basically just means that all of their angles are less than 180 degrees. And this becomes important later on when we define the linear matrix inequalities. And the bounds, if we look at this sort of 2-dimensional example, this cube or this square has 4 hyperplanes, right? So this is one hyperplane, this is a second hyperplane, this is a third hyperplane, and this is a fourth hyperplane, right? Because there will be one for each bound in each dimension. So that's why a 2-dimensional hypercube will have 4, right? So 2 times n-dimensional hyperplanes. So because this is a 2-dimensional cube, the hyperplanes will be 1-dimensional, right? So this makes sense. If we think of this as the x direction and this is the y direction, we'll just have like, a minimum x value and a maximum x value. That's 1-dimensional, and a minimum y value and a positive or a maximum y value. So this is easy to understand in the 2-dimensional space. As I'm sure you guys have experienced on your own time, data is very rarely 2-dimensional when in most applications where you would use a neural network. So all of what I'm saying, all of these principles apply to higher dimensional hypercubes. So no matter to what dimension you scale this, all of these ideas still maintain and hold true. It's just that it's a lot harder to think of in like n dimensions. So we're going to stick to mainly 2- and 3-dimensional examples. So now that we know what a hypercube is, the question is, how do we get from the input space to a topological covering using hypercubes? So how do we create this sort of shape here with hypercubes? Now, again, in this dimension, in this example, it seems trivial, but again, data is multidimensional and it will never be, you know, dispersed like this. You will always have interconnected regions. You'll have blue dots within the red dots and red dots within the green dots. So this is, again, just to illustrate how this process basically works. So one way to do it is covering with uniform hypercubes, right? So you just cover everything with a hypercube of the same size. And the way it works is with a pretty straightforward algorithm, right? So if NT is all of our training points across all categories, we are going to construct a set of bounds. So a lower bound and an upper bound across all J dimensions, right? So if you think about that, you go into dimension 1 and you scan through all of your data points and you find the smallest value in that dimension, and you also find the largest value in that dimension. Those are then your lower and upper bounds for that dimension. And you just repeat that process across all dimensions, right? And like we saw here, right, if you have a minimum value and a maximum value in each dimension, that directly specifies the bounds for a hypercube, right? So if we do this process, find the minimum and and maximum bounds in every dimension, we directly specify a bounding hypercube, which we're going to call HT, right? So it's important to note that this HT, this encompasses all points across all dimensions within our entire training data set. Now, if we define a value L, which is less than the smallest distance between any two intra-class points in the data set. This intra-class points is very important. So I'm going to go through the data set and we're going to compare every single point across classes. We don't care about points within the same classes. We just want to know, of all the classes in the data set, what's the smallest distance between 2 points that have different classes. We're then going to take a value that's slightly less than that distance, and we're going to divide our original big hypercube into smaller hypercubes by dividing each dimension into bins of width L, right? With each of the resulting hypercubes having a value L to the n, right? So you're basically just going along each axis and chopping it up into sizes of piece L. The resulting set of hypercubes, which we're going to call H, represents a complete covering of HT with no overlapping regions or empty space, right? So this set of hypercubes covers the same region as our original hypercube, HT. And because we were smart when we chose L, right, we chose it significantly small or sufficiently small, each member hypercube, right, so each AK within this general H, each of the smaller hypercubes can be classified unambiguously as either empty or containing points from a single class. So all of this might sound really complicated, but it's actually really simple when you look at an example. So this is our data set, right? We begin by finding the lower and upper bounds in both directions, right? So B1 and right, so B1 less than, B1 greater than, and then B2 less than and B2 greater than. These are our bounds. This shape right here, that's our hypercube. That is this HT, right? Pretty straightforward. We then go through the data set and we find the smallest distance between 2 points of different classes, right? So it looks to be about this one, although some of these look like they might have similar ones, right? But you can see that I intentionally made this line segment slightly smaller than the distance between these 2 points. And that is, again, if we want to make sure that each of our cubes, right, has either a uniform set of points or is empty, this distance needs to be smaller than the distance between these 2 points. So now that we have L, right, we chop up the original hypercube across all dimensions into cubes of size L, or L to the n. So in this case, it would be L squared because it's 2-dimensional. Each of these cubes, right, can now either be belong to a specific class or is empty, right? So here we have an entire covering of our original space, right? It looks like there's some white space, but these are still hypercubes. It's just that they're empty. They don't belong to a class, right? So there you go. The problem is that this scales very, very poorly because the total amount of cubes you require for a uniform covering, which we're going to call K, is directly proportional to this equation here, 1 over L to the n. So if we just think about 2 examples here, right, let's say L is, let's call it 0.1, which for real world data, especially if you normalize it beforehand, is very reasonable, right, that the distance between 2 points might be 0.1. And if we say n, the number of classes or the number of dimensions is 32, which again is extremely reasonable, you know, for real world data, this number, this is 10 to the 32, right, which is huge. So it's not really possible to scale this algorithm well, especially because that example we just went to, the 10 to the 32, that's still on the reasonable side of data, right? There is data that has like 10,000 dimensions, right? And where 2 points of a different class might be way, way, way closer than 0.1. So this algorithm doesn't scale well. One way to get around this is to notice that this L level of granularity, it's really only necessary along the decision boundary between two classes, right? So between sort of this, in this region right here where blue transitions to red, this L distance or L granularity, it's necessary here because we need to distinguish that. But within these points here, these cubes don't need to be that small, right? Because this is an entire uniform region. We could make this entire region one cube, right? Which would drastically reduce the number of cubes. So one way to get around that is by using a bisection algorithm. So again, we start with HT, which in the original example is the same thing. It's just the uniform covering of all our cubes. And then we bisect this cube along the axis of most benefit. And the way you determine the axis of most benefit is you look at every single axis and you say, what degree will this bisection homogenize the distribution of point classes in the resulting daughter hypercubes, right? So if I bisect a cube in one direction, what is the homogeneity of the points within each of the resulting hypercubes? That's how you can determine which axis to bisect on. And then you basically just repeat that process for all of the daughter hypercubes recursively. So we're going to keep doing it until the daughter hypercubes have a uniform set of points in them, right? So all the points in the cube are the same, or until we violate a minimum length scale, which again has to relate to the distance between 2 points. But this isn't really worth going into. So again, it sounds kind of complicated, but when you look at an example, it's actually pretty straightforward. We start with a set of points, right? We compute the lower and upper bound in each dimension. This defines our original hypercube. And then we look and say, okay, which axis should I bisect along, right? So if I bisect along axis A1 here, I'm going to end up with these two cubes, right? This upper one and then this lower one. Now, these cubes are not homogeneous, right? Because this cube will have red points and green points in it, and this cube will have red points and blue points in it. If, however, I bisect along the vertical axis, right, this resulting cube has a homogeneous distribution of points in it. It's only red points. This one still has two different set of points in it, but because one of the resulting cubes is now homogeneous, it's better to bisect along this axis, which is exactly what we do here. And now that this cube has a homogeneous set of points, we no longer look at it during this recursive process, right? So there's no need to bisect this cube any further because all the points within it are the same. This cube, however, will go through the same process. So we repeat until all the cubes are uniform, or until the bisection, or until bisecting the remaining heterogeneous cubes would violate the minimum length scale, right? So one of the issues with this algorithm is that you end up getting these sort of narrow one-class peninsulas, like these regions that shoot into one of the other areas of one of the other class areas or one of the other hypercubes, right? So basically places that have high aspect ratios. That's one of the problems. Another one of the problems is you don't get a full covering, right? There are these spaces, these blank white spaces, which haven't been assigned to a class. And what's worse, you have white space, right, within a region that arguably is relevant to the parameter space, right? So you could argue that out here, because there's no points, it's not maybe super important that we assign a class label here or even here, but these sort of white regions in here, they clearly exist in relevant parameter space. So they should be assigned a value. Another problem with this is that it usually overfits the training data and doesn't generalize well, which is pretty obvious when you actually look at this graph. This looks like it's overfitting the data. So one way to get around these issues that are listed here is just restricting the aspect ratio, right? So we're going to restrict the aspect ratio. So when we go to bisect a cube, right, bisection can only occur along directions such that the resulting daughter cubes don't exceed the maximum aspect ratio. ratio, right? So each time you go to do a bisection, you check to see what the size of the resulting cube would be. And if it violates the aspect ratio rule, you don't do it. Now, this method sometimes prevents more optimal bisections from occurring, which makes sense because we're restricting it, but it scales much better to unconstrained bisections, right? So this generalizes a little better and the algorithm works a little better, especially because you end up with less hypercubes when you do it this way than you do the other way. The only problem that exists with this method, which was also existing in the previous method, but it's still something we have to deal with, is that you get these empty white spaces, right? And this entire square region, right, or rectangular region, it belongs to our parameter space. So we want every region within it to have a class category, right? So one way of dealing with that is just, reducing the complexity via the classification porosity, which again sounds complicated, but basically all we do is we go to an empty cell like we do here, right? Like let's say this is a cube, and we say, we look at the border area, right, with non-empty cells, and that cell gets classified as whatever its maximum boundary area is, right? So if it's touching two cells of different classes, whichever one it's touching more is what will get assigned. And again, we repeat this recursively until we have no more white space, because within this region, you can't see it, but there are probably multiple hypercubes, some of them in the middle of this white space, and you can't classify that one until we've classified the ones on the edge. So you just repeat this process recursively, and then voila, we have a full covering for our entire parameter space. And it's important to note that this algorithm actually scales pretty well, right? So they tested it up to 32 dimensions, and it turns out that the computation time scales with the number of points in the point cloud rather than with the dimensions, right? So if you have the same number of points, right, and you increase the dimension 2, 3, or 4-fold, there's not much of an increase in computation time, right? I mean, there is, but it scales more with the number of points rather than with the number of dimensions, right? So now we have our covering, right? Now we have our covering, however many dimensions we want. So the question becomes, given that we now have our covering, how do we get from here to this set of linear matrix inequalities? And it turns out it's actually pretty straightforward, right? And this has to do with some of the characteristics of the hypercube we talked about earlier, right? So hypercube convexity allows the interior to be delineated by a logical combination of inequalities, one per bound. So because all of the angles are less than 180, in each direction, we can say everything within this hypercube is going to be greater than this value or less than this value. Additionally, because the bounds of a hypercube are defined by simple hyperplanes, the inequalities are linear. They're not quadratic or cubic or anything. So for a given hypercube, right, HK, right, when we talk about HK now, we're referring, for instance, to one of these specific cubes, right, or one of the specific cubes that is the outcome of our bisection algorithm. For specific cubes, the set of boundaries, right, less than and greater than, right, for each dimension can be translated into a matrix of weights and vector biases. And the way you do it is pretty straightforward, right? So for each of the constraints, the upper bounds have weights 1 on the diagonal and biases of the negative upper bound value. And then it's just the inverse for the lower bounds, right? So the n constraints corresponding to the lower bound, right, have weights -1 on the diagonal and bias and just the normal bias value. We don't invert the value. And with this sort of one-to-one relationship, you can construct these sort of weight and this weight matrix and this bias vector, right? And these equations, and we're going to go through an example later so that you really understand the weights and this inversion, but these should look kind of familiar for you because they pretty much directly look, it's a linear combination of weights, inputs, and a bias term, which is basically the direct input of an activation function, right? So this system of inequalities is analogous to the input of a hidden layer. And if we use a ReLU activation function as our activation function, Z, right, this activation is just the ReLU of these individual, of the weight matrix multiplied by the input plus the corresponding biases. And it's important to note that this ReLU is applied element-wise across the output of this computation, right? So you're going to get an output for each bound in each dimension. So ReLU is applied to each one of those individually. Also, I don't know why they did this in the paper. I don't know why they wrote ReLU here, because it's not actually the ReLU function. They say ReLU is x times theta x, where theta x is the Heaviside step function, right? So the Heaviside step function, there's a couple different forms, and the only way they differ is with how they deal with x equals 0. But in general, in the paper, the way they use it is if theta x equals 0 if x is anything less than or equal to 0, and theta x equals 1 for any x greater than 0, right? So it's just a stepwise function. It's pretty straightforward. And again, it's important to notice that ReLU x equals x times theta x. So x here is our entire input here. So we're going to have the entire input here multiplied by theta of the entire input. And again, we're going to walk through an example. It'll become much more clear. This here is for a single cube, right? So for a single cube, right, we want to sum over all of the constraint dimensions, right? Because a single cube is going to have multiple dimensions, right? So we define big theta for this cube as that summation. And this theta k, right, because of how they, or sorry, theta x, because of how they define the ReLU function, will take on a value of 0 if all of the constraints are satisfied, and a finite value if at least one of the constraints is not satisfied. So basically, if the point lies within this specific hypercube, then this equation will equal 0. If the point does not lie in the hypercube, so if it is outside of one of the bounds in one of the dimensions, then this function will take on a finite value. So finite being an integer value greater than 0. Now that we sort of define this, we have to go one step further, because this is for a single cube, you know, and if you go back and you look at the example, there are a lot of cubes in here, right? So how do you combine all of this, right? This individual equation has a one-to-one correspondence with a neural network, right? That has n input nodes, right? N for the dimensionality of the input, which is represented by x, and then 2n hidden layer nodes, right? Because for each of the dimensions, right? So for each value of n, we need an upper and a lower bound. So that's why it's 2n hidden layer nodes. If the output of this hidden layer node is then summed, right? So if it's combined and fed through the ReLU, like we just saw on the previous page, so we take it and sum it and feed it through a ReLU, and that second layer, right? It just has, you know, a uniform weights of 1 and a bias of 0, because all we're interested in is the output of the ReLU. If we have k hypercubes, right, that cover a region in the parameter space that correspond to a specific region, right? So again, if you look at this example, there are multiple cubes that are of the color orange, right? So for a single point, we want to know, is this point within any of the orange cubes, or within any of the green cubes, or within any of the blue cubes, all right? So if there are KC hypercubes that cover a region in parameter space that correspond to a specific class C, then there are KC corresponding functions, theta KC, right? So this equation we saw on this page here, you'll note this subscript K refers to a specific hypercube. So we have an equation like this for every single hypercube, right? And each of these functions independently corresponds to a hidden layer topology with uniquely defined weights. So we can then take these KC hypercube functions, right? So all of these thetas, and we can combine them in a way such to, right, which is what this big theta function is, right? And we can come with, you'll note this subscript or superscript C here. This refers to this, again, corresponding to a single class. So again, referring to that earlier example, this is, for instance, the function for all orange hypercubes or all green hypercubes, right? We can combine the input functions for each hypercube in such a way that this function is approximately equal to 0 if the point lies on the exterior of all KC hypercubes, or it is approximately equal to 1 if it lies within one of them, right? So this function, this is basically the output that you want for each class. And you can then take these and then combine them in sort of a softmax style to say, which one of my classes does my input point belong to, right? So this would sort of be an example for a single what you see here is one of these theta k equations, right? So this theta superscript c subscript k, this is corresponding to a single hypercube k, right? And that's what you have here. So this is our input, 3 dimensions. You'll notice that this hidden layer has 6 nodes, right? Because for each of these dimensions, we need an upper and a lower bound. This right here, this set of constraints is for a single hypercube. So you have multiple of these, right, to equal or produce this output. This output here would be the equivalent of this theta superscript c, right? So this is the combination of all hypercubes, right, that belong to a specific class. Now, it seems a little confusing, but it's actually pretty straightforward when we walk through an example, right? So we're going to do this in 1 dimensions just to simplify everything, right? So I have 3 classes or 3 points belonging to the red class and 3 points belonging to the blue class, right? So let's say I want to define a hypercube to capture these, right? For the red class, right, which everything that has a subscript red 1 obviously refers to the red, and everything that has a subscript 2 blue refers to the blue points. So the lower bound of the red hypercube would be -4, right, which is here, and the upper bound would be -1, right? So again, the weights, because this is a 1-dimensional example. Oh, wow. Sorry, this should say 1D up here. That's a mistake. Sorry about this. This is a 1-dimensional example. These weight matrices, right, these would usually be n-dimensional, right? So if this were a 2-dimensional example, this upper part of the matrix would, for instance, be 1, 0, and 0, 1. So it would just have 1s on the diagonal. And the lower part would have -1s on the diagonal. But again, because it's 1-dimensional, this matrix is 1-dimensional, and this matrix is 1-dimensional, right? So upper bounds, right, have 1 and -1, like we talked about up here, right? And the bias corresponding, right, to the upper bound, we invert. The bias corresponding to the lower bound, we leave just normal, right? And so the same thing for the blue example. Weights 1 and -1, right, for the upper and lower bound respectively. And then we take the upper and lower bound and we invert the value of the upper bound and leave the lower bound the same, right? So weights 1 and -1, biases 2 and, these are the bounds, right? So we have biases -4 and 2 corresponding to the upper lower bound. And then the same thing up here. So let's look at an example, right? Let's say x equals -2, right? Again, remember earlier that this theta here, this is a Heath side step function, right? So when we look, and it's applied element-wise. So we apply this to each of these upper and lower bound weights and corresponding biases, right? So -2, right, times 1, because we have this weight of 1, plus 1, because our upper bound bias is 1, which is the inversion of the actual upper bound, right? This equals theta of -1, right? Which just equals 0, right? Because Heath side step function, anything less than or equal to 0, we're just going to truncate at 0. And the same thing for this one, right? So -1 times -2 is 2, -4 is -2, and the Heath side step function of -2 is 0. Now, these are basically the ReLU functions, right? So the theta corresponding to this hypercube, which in this scenario actually also corresponds to the entire class because we only have 1 hypercube, but theta of this cube is x times theta x, right? So you'll notice that our x here simplifies to -1 and theta x is 0. So we have -1 times 0 plus -2 times 0, right? Because again, this is a summation over all of the bounds, which equals 0. And this makes sense because this function is supposed to take on a value of 0 if all the constraints are satisfied, which is another way of saying if x lies within the cube. And you see x is -2, -2 definitely lies within the bounds of this cube, right? So now let's look at the blue example, right? Again, x is -2, and we do the same math, right? So the weights again are 1 and -1. So 1 times -2 is -2, -4 is -6. So Heath side step function of any negative number is 0. The lower bound, however, or the, right, -1 times -2 is 2, plus 2 is 4, right? And the heave side step function of any positive number is positive. So this now equals 1. So when we compute our big theta, we have, again, x times theta x. So we have -6, which is this x, times 0, which is the output of theta x, and then 4, right, times 1, because the output of this is 1. So you'll notice that this is a finite value, which indicates that this point x does not satisfy at least one of the constraints of this hypercube. Now, there's one small thing to note. I think they just left this out in the paper, or you're just supposed to assume from this graph. If you look at this function here, right, they say that big theta of c, so this, should take on a value of approximately 0 if the point x lies on the exterior of all KC hypercubes, and 1 if it lies within one of the hypercubes. This value right here, this theta superscript c sub k, this is what we just computed here, right? The problem is that you can't use 4 as a value in that equation, because if you go back and look to it, you're supposed to compare it to 1. So I believe the output of this is again supposed to be run through the heave side step function, which would then truncate this at either 0 or 1, which then makes sense working with this equation, because this would then take on a value of 1 or 0, right, for the blue cube, indicating that the point lies on the exterior, and 1 for the red cube, indicating that the constraints are satisfied and that the point is on the inside of the cube. So, you know, it seems sort of complicated, but when you boil it down to a one-dimensional example, and again, I'll correct this title, this should be 1D, it's actually pretty straightforward. And again, everything I've presented so far extrapolates to higher dimensions. So while this is a 1D or sometimes 2D examples, all of this holds true for 3D and 4D and higher dimensions, right? So they designed this algorithm, and one of the things I mentioned in the introduction was that there has to be a slight disclaimer on how they compare it to results, right? Because we're dealing with straightforward multi-layer perceptrons, right? There are no like benchmarks in terms of saying this is the ground truth. So they have to design, you know, a neural network that they're going to compare it with. And so they went through a number of sort of iterations, right? Between 1 and 3 hidden layers, and between 8 and 128 nodes per layer. And they noticed that the simple classification problems, for the problems they explore here, changing these variables didn't really have a huge effect on the outcomes. So they just decided on a network with 32 hidden nodes, right, as a benchmark, right? So a single layer with 32 hidden nodes. Now, what they compare here on the left is, this is the hypercube bisection algorithm, and this is the traditional neural network. And like I mentioned earlier, the training for the hypercube is the actual bisection process, right? It's actually going through and computing your topological covering, because once you have your covering, that's it, right? The covering corresponds to linear matrix inequalities. Those linear matrix inequalities correspond one-to-one with neural network hidden layers. And like we walked through in this example, if you use those weights and biases that come out of those linear inequalities, there's no training on the network side. So when they present clock time here, this is how long it took to do the bisection, right? So they present findings on 3 data sets: the iris data set, the wine data set, and the MNIST data set, right? Iris is just dealing with certain plant portions or certain areas of a plant, like stamen and things like that. The wine data set is just about, it has a bunch of different, you know, attributes of wine, like alcohol content and sulfate content and all sort of that. And I'm pretty sure everyone's familiar with the MNIST data set, right? So this obviously is a graphical data set, right? And because this is a multi-layer perceptron, you cannot feed in 3D data. So as you see, they perform PCA on all of these, right? Because although this algorithm scales well to higher dimensions, PCA allows you to, you know, use a smaller set of dimensions while not really sacrificing any accuracy. And you'll see here that across the entire accuracy, right, bar the MNIST data set, for the iris and wine data sets, the accuracy of the hypercube algorithm is, you know, significantly higher when compared with the iris data set. somewhat higher when compared with the wine data set, and roughly even when compared with the MNIST data set. However, the standard deviations, right, because these results are presented across 20 training and evaluation iterations for both the Hypercube and the traditional network results. So the standard deviations for the training, the neural network one, were much, much, much higher, right? And that's one of the things we talked about earlier, where we said a lot of times, even if you use the same topology and initialize the weights the same way, depending on how your batches are randomized and things like that, you will end up in a significantly different area in the in the optimization space, right? Which is why the standard deviations here are much, much, much higher. Additionally, the clock time, right, for the bisection algorithm on the iris data set is significantly lower. It's roughly about half or less, right? The wine, the bisection algorithm is a little bit higher, right? And then for the MNIST data set, obviously the bisection algorithm, it takes a lot longer just because, again, this algorithm does scale with the number of points and not necessarily the number of dimensions. However, when you increase the dimensions, you do also increase the complexity of the algorithm. So it does make sense that this would take a little longer. But again, big disclaimer, if you were actually trying to do this with neural networks, you would use a deep neural network, right? Like you probably wouldn't stop at 3 layers. And, for the iris and the wine data set, you would probably go significantly deeper than 3 layers. And for the MNIST data set, you would use a convolutional neural network, right? Which, gets, excuse me, which performs much, much, much better. So that's why this entire paper should sort of be taken with a grain of salt, because while I do find it interesting, while it is a very interesting concept, this is it, right? Like there's nowhere to go from here. You can't add more layers. You can't do anything. So what you see is what you get, right? And while they compare it against, 1, 2, and 3 hidden layer networks, if you were to actually use a deep neural network and add potentially some more complicated features like skip connections and things like that, you would probably significantly outperform their results, at least in terms of accuracy. Clock time probably would still take longer, especially as you increase the complexity of the network. But again, very cool idea. Sort of has its limitations because everything they do with their comparisons on the results is using a very, very simple network. And yeah, that brings us to the conclusion. So traditional iterative deep learning training approaches, right, like backprop, require intensive training and extensive computational resources. And a quick disclaimer, deep learning here is, they use it in the paper. I'm not really sure I would say this is deep learning, right? Because, usually you'd have a lot more layers than just 1, 2, or 3. So an alternative to this iterative approach is using the data topology and geometric methods, right, to train, again, deep with a little star here because they're not really deep. And the main reason this works is because there's this fundamental relationship between a linear matrix inequality and their ability to bound the shape of a data. And there's also this fundamental relationship between a linear matrix inequality and a rectified linear unit activation function when used in a neural network like this. So that's it. Any questions?
Hey, Konstantin.
Mm-hmm.
So I'm just wondering, how is this any different from just using back trees? So basically random forest.
Yeah, no, I actually noticed that too. When you can literally, if you create a decision tree that basically follows sort of the process you use in the bisection algorithm, right? Like it's the exact same thing. It is literally the exact same thing. Because you're just saying given a point, is this dimension greater than this value or less than this value? Okay, then we go here. Now is this dimension greater or less than? So it is literally the exact same thing. I think it would have actually been interesting to compare these results with a decision tree because it's the exact same thing.
So basically they just rediscovered random forest without bootstrapping and said that it's better than a shallow network on these particular data sets.
Yeah, that's basically what they did, which is again why I said take the whole paper with a grain of salt, because while it is interesting, while this concept of using hypercubes to construct a data topology, this is very interesting, but this is literally like the definition of a random tree, right? It's just saying, is something greater than this or less than this? Okay, then we go here, and eventually you'll end up at a node that has a specific class label. So it is the exact same thing, yeah.
Yeah, and I mean, also the results seem really strange. So 24% standard deviations for like neural networks. I never got like such high variance when I was training. Like, yes, results differ with like different initializations, but never by that much. That just seems really strange to me.
Yeah, I thought that was strange too. And I'm just trying to remember right now if they say, I think they tell you how many epochs they trained for. I think that was one of the issues because I'm not sure they trained it to convergence, but I can't find the specific amount right now. But I have a hunch that that's one of the reasons why there are such wild standard deviations here, because they didn't necessarily train it to convergence or use a stop criteria that was specifically designed to make their method kind of look better.
Yeah, makes sense. Okay.
Yeah. Anyone else? All right, good stuff, guys. I'll post a link to the presentation in the Slack. I just got to change one or two things like this and had a mistake in here. Sorry for that. Yeah, if you have any questions, just reach out to me on Slack and enjoy your day.